Good morning, good evening. Welcome to the next series in AI Foundations, Module 3, Session 3. Today's topic is going to be around machine learning types. So we've probably heard a bunch of supervised and unsupervised and maybe reinforcement learning. And so today's session, we will dive deeper into that. So our instructor for today is Parul Pandey, and I'm going to pass it over to her.
Thanks, Rafael, and welcome back, all of you. And welcome back, yes, to yet another session of AI Foundations, Introduction to Machine Learning module. I hope I am loud and clear. And
Great.
Yes, okay, thanks. So, well, yes, so we've come into this third session. The last week, we covered 2 sessions, and we'll be covering 2 sessions, including today's, this week. The next one is on Thursday. So let's get started. So before going further, let's just revise what we did in the last 2 sessions. We started this module of machine learning with understanding how do we convert our business problems to machine learning and AI problems. We went over the requisites, we went over the steps in which we can create good machine learning problems, and understood the merits and demerits also. In the second session, then we went a little further and we delved into the workflow, the data science workflow, right from data collection to model creation to training, and then being able to explain your results. So both the slides and the sessions, the recorded videos have been uploaded, and you can go out and check them if you want. So what do we have today? So today we come to this interesting bit where we will study about the types of machine learning. And we're going to go over the 3 most common types, which are supervised, unsupervised, and reinforcement learning. And we will also understand some use cases, typically business use cases, where these learnings are utilized. And then we'll summarize everything with understanding what we covered and what we will cover next. For the next session, which is to be held on Thursday, we're going to understand what is ensembling, and we'll go into the world of automated machine learning. So don't forget to tune in this Thursday too. So let's see what do we have in our schedule today. So machine learning is rooted in statistics, and it allows us to take information like data and extract some insights from it to create some business value. So this is the most accepted machine learning definition, and I think by this time we already know what it means. Now, what is interesting is it is divided into subcategories based on what type of problem is appropriate for the method. So in this session, we will learn about some core aspects of each type of machine learning. We'll discover some popular algorithms in each category, and we shall also review some common problems that can be solved by each approach. Now, I again want to highlight that we are not going to delve into the code or implementation of the algorithms. That we shall cover in our next foundation course, that's Machine Learning Foundation. But what you can take from this session is you will have an understanding as to what algorithms are and how do the different kinds of algorithms differ in their idea of implementation, and what are the principles on which it is based. So this is going to be the main key takeaway from this session of today's. Let's start with the first part, which is the types of machine learning. Now, if you remember, in the last session, I explained to you what a model is and how a model is different from what an algorithm is. So we'll just go back to it. It's just a quick revision, just so that the idea gets reinforced. So the general idea is we create models and then we feed data into these models, and we generate outputs. Simple. Now, these outputs, they might be predictions for future trends, for example, predicting the stock prices, or it could be finding patterns in data. Now, this model, the square, the cube that you can see, is some sort of a self-contained package, and that will take the features computed from the input data, and this will produce a prediction or a categorization, depending upon the problem, and some metadata. Now, this package, the package called model, can take many forms, but what it always includes is a mathematical representation, a code, a business logic, and training data. And whatever it predicts, all the predictions, they are then consumed downstream by systems or users or applications. So this is the whole concept of a model. So it's just a mathematical representation. Now, how a model differentiates is different from an algorithm is that an algorithm is essentially just a set of rules. So it's a set of rules which actually tells a computer how to solve a particular problem. For instance, we have regression algorithms, we have classification algorithms. But a model is something that you would build by using this algorithm. And you would create a model. So you have a regression algorithm, and you can use this algorithm to actually create a model to predict the sale prices. So the model is this, you could say the whole composition, and algorithm is a part of it. Now, these two are very important concepts, and why I'm going over them again is because today we are dealing with algorithms, and before you delve into algorithms, you should be clear about the difference between algorithms and models. Another important concept to be revised before going further is what is features and what are labels. So for instance, for this data that has been shown on the screen, the features are the descriptive attributes. So for instance, these are the features of a person who is applying for some loan in a bank. So his age, his or her age, historical bill amounts, the payments made, the balances, these are all the descriptive attributes of that person. And what a model has to predict is whether the person is going to make the payment or not. And this is the label. So label is something that we are attempting to predict or forecast. So having just revised all these things, let's also try and understand a very important concept of training and test data set. Now let's say we've got a machine learning algorithm and we feed in some data. Now let's just say it's some data. And let's call it training data because we are going to train our model on that data. Now this algorithm will produce a classifier, and it's just a basic machine learning situation. Now, let's say we want to deploy this model of ours, this classifier. Now we need to test it with some independent data. Of course, there'll be new data that will be coming in. And we will evaluate. This will tell us how good our model is, how well it predicts on some new unseen data. And once we see that, yes, it is giving us good results, I think it is the time to deploy. Now, you have to understand that you will only get reliable evaluation results if this test data is different from the training data. In no situation can these two data, training and test data, be the same, because that will be a false evaluation. Of course, if you use the same data for training and the same data for evaluation, you will get great results, but your model will fail on any new unseen data. So both the training and the test data have to be different. But the problem comes when we only have one data set. We don't have different data sets. So how do we test our data set, test our model? So in that case, we divide our training and test data sets. So we take that chunk of training data and we divide it into like some parts, perhaps 2/3 of it for training and 1/3 it for testing, or 80% for training, 20% for testing. And then the 80% of data will be used for training purposes and the rest of the data will be used for testing purposes. And that's the concept of training and testing data. So sometimes this test data is also called validation data set because you validate your model on this. And when you get some unseen data, that is called the test data. So these are different names which are given to it. But it's just important to understand is that both these data sets have to be different. Now, having known all these concepts, let's start with what we have come here to study and know about. That's the major types of machine learning. The three most common types of machine learning today are supervised learning, unsupervised, and reinforcement learning. So what is supervised learning? Supervised algorithms, first I'll just go through the technical definition of what it is, and then I'll just break it down. So supervised algorithms use labeled data in which both the input and the target outcome or the label are provided to the algorithm. So what does this mean? What does it mean? For instance, you have these inputs, and for every corresponding input, you also know the output beforehand. Now, what happens is, what could be a classic situation for this is, for instance, you are in a bank and you have data of all your customers for the past 6 months, and you know that for every customer, you know whether they repaid their loan or they did not repay their loan. You know all about this. So what you do is you feed that data into your model, and the model is going to train on that data and it will learn some patterns. Once it learns some patterns, it will then apply those patterns to some new data. And for instance, there's a new customer who comes to your bank, you absolutely do not know about that person. You ask him to fill up a form and he fills in some data, for instance, his age, his past, his historical payment history, or what is his current income, what are his family members. And all this information, you take this information now and you predict whether this person will pay, or what are the probabilities of this person paying the loan or repaying the loan. So for such a problem, you knew the historical data, you knew the labels, you knew the training set and the corresponding labels, and you used it to predict outputs on new input data. So the classic examples for this are predicting housing prices. So based on your historical data, you can predict what will be the housing price for a new house in the locality. You could also predict the interest rates. Now, why this is called supervised learning is because you could say in a way the machine has a supervisor or maybe a teacher. Now, this teacher gives the machine all the answers. So you can just consider a hypothetical situation that there is a teacher and there are some students. And so what the teacher does is he or she gives the machine all the answers. So for instance, it will tell whether it's a cat in the picture or there's a dog in the picture. So it gives a picture and says, this is a cat. It gives another picture and says, this is a dog. And it gives millions of such images. Now, the teacher has done all the work. The teacher has already divided, or you could say labeled the data into cats and dogs. Now, then this machine is going to use these examples to learn. And once the machine has learned, if you give it a new picture, the machine will identify whether this image belongs to a cat or a dog. And hence it is supervised. So there is a supervisor. How it works, like I told you, you have a training data. So there's a bank that's trying to use machine learning to figure out if someone's going to default on a loan or not. So the data set provided is of credit card transaction of the person, say for the last year. So on the left-hand side, you have the credit card transaction of one person for last year. And using this data set, the model learns the patterns between the label and the other features. And then it will create a model to guess whether it will default for the next 6 months or not. So that was supervised learning. The next kind of learning is unsupervised. And I think the name itself suggests that there's going to be something different from supervised. And what is going to be different is that you do not have labels for your data. Let's see. So unsupervised learning is that type of machine learning that looks for previously undetected patterns in a data set and has no pre-existing labels and with minimum of human supervision. So like there's no human supervision, hence unsupervised. So unlike supervised learning, we do not have a variable to predict. We have nothing to predict. We do not want to predict whether it's going to pay the loan, what is going to be the temperature next day, or what is going to be the sale price after 30 days. No. So what we try to do is we try to uncover some hidden patterns in the data so that we can identify clusters or groups within that data. So you could see that an example here could be there's a company and there's a big company who's into selling clothes, and it wants to segment its customers. Now it wants to group them depending on their age, on their income group, so that it could better understand them. It would have an idea what age group buys what kind of clothes, what age group splurges more, what age group returns more any product. So this means the machine is sort of left on its own. And if we just recollect the example of the cats and dogs that I said, you could think of it like this. You have this huge pile of animal photos. You don't know which one belongs to which animal, and you just throw it at the machine. And the machine has to now figure out what pattern it can see in that pile of photographs. So if you see this example, you'll see how a classic unsupervised machine learning algorithm works. So for instance, there's a company which has the customer purchase data for a lot of customers. Again, this could be like millions. And you feed in that data into this unsupervised algorithm, and this algorithm then recognizes patterns in this data set. For instance, it has segmented this data set into 3 groups. If you can say there's a yellow group, there's a green group, and there's a red group. Now this could be anything. Maybe for this case, we could say that the green group are the people who are the ones who buy the most expensive products, always. The red group are the ones who would always return their purchases after 2 or 3 days. And the yellow ones are the medium earning people who buy reasonable products. Now this group or the clusters that this machine has found has been done it on its own. There has been no human intervention. So once this machine recognizes this pattern, for instance, we have new customers. We have the data of purchase data of new customers into a catalog. And when we use the same model on them, we'll also find another group. And you could again see that for new customers also, it has separated them into exactly same groups. So again, from that new data, again, we could find out one group who splurges most and one group who are the most dissatisfied group. How does it help a company? When you know that there are a group of people who buy or a lot of high-end products, you could target your marketing towards them. You could send them newsletters, letters of the arrivals of new products, high-end products, for instance, flagship phones. And for the people, the dissatisfied lot, you will try and understand why they're dissatisfied and why they're giving bad reviews to products and how this is hampering the reputation of the company and how you want to tackle it. So this is what happens during unsupervised learning. And this example that has been shown to you is a classic example where unsupervised learning is used in the industry today. So we've completed two kinds of learning, unsupervised and supervised, where they're sort of related in the sense that you have features, you have data, you have a model, and then depending upon what type it is, you either have labels or you don't have. There is a third kind of learning too, which is called reinforcement learning. It's slightly different from the other two, because what happens in this learning is that an algorithm learns to perform a task simply by trying to maximize the rewards it receives for its actions. So what happens is, here we have an agent, or you could say that agent we have. Firstly, this kind of learning is used where we do not have lots of training data, and the only way to learn is by interacting with the environment directly. So we have a training agent over here, and it interacts with the environment. And when it interacts, it either gets rewarded for its actions, or it gets punished. So over the period of time, through repetitive learning and interactions, it learns how it should perform to get maximum rewards. So that's a very good example. And we've all heard about this video game called Mario. And if you look here, this is a neural network which is actually playing this game. Now, there is no human which is sitting behind this. This is being done completely by computer. But the computer did not know how to play this game so well initially. But what happened is, over the period of time, it learned that, if it went forward or, it sort of jumped, it was getting rewarded. So it might be getting +1, +2. And every time it went the other direction, it was getting penalized. So it learned how to get the maximum rewards. And so it started playing this superbly, even better than a human. Where is this reinforcement learning used? I think we have examples in front of us in the form of self-driving cars, robots, games, video games, and even automated trading. So this actually means surviving in an environment. Okay, so the core idea behind reinforcement learning is just survive. And you just throw some robot into real life, you punish it for errors, but you reward it for right deeds. And I think this is in some way related to how we teach our kids. So we sort of give them a chocolate for everything that they do correctly, and we sometimes scold them for not doing things correctly. And it's the same concept. We went over, or we took an overview of the three main kinds of machine learning that is used today: supervised, unsupervised, and reinforcement. We haven't touched on the algorithms, which we will do now in this part, but we now have a general idea about what they are. In this part, let's go over some of the most commonly used algorithms in the categories. Let's start with supervised learning, because I think this is used a lot. And this is pretty much used in banking, in insurance sector, in health sector. Now, this supervised learning again is divided into two kinds of problems which it encounters. And that differentiation is based on what is the final outcome, what we are trying to predict. So supervised learning could be classification if you want some category. So for instance, if you talk about sentiment analysis, where you understand the polarity of a text. So for instance, whether a tweet is positive or a tweet has a negative sentiment, or even a tweet has a neutral sentiment, So this is a classification problem. Again, whether a person is going to default on a loan or not, again, this is also a classification. So you are trying to find a category. It could be binary, it could be multi-class. So you have categories and you try to put your outcome into one of the categories, like a yes or a no. Regression problems or regression supervised learning are the ones where you predict a numerical value. So the final value has to be a number. You predict the sales of the company, sales of a quarter. You predict the profit of a company. You predict the interest that you would have to pay. So all these are numbers. And such problems where the outcome is a number are called regression problems. Now, let's see what are the different types of algorithms that we can encounter in supervised learning. Let's start with one of the most highly interpretable standard method for modeling the past relationship between the independent input variables and the dependent output variables, and that's called linear regression. So it has a regression term in its name, so this clearly tells you that it is used for regression problems. So, for instance, you have a height of few students on the x-axis, and you have their corresponding body weight. And for instance, you have like 6 of them, and you plot them on a graph. So you get a two-dimensional graph. And what you try to do in linear regression is you simply draw a line that sort of indicates the average correlation. So when we had all these asterisks, which represents data points, we try and draw a line which would give us an idea about how the weight is related to the height. And you could here say that it's sort of positively correlated. So more the height, more would be the weight. This is what we can infer from this graph. Now, if we get a new data point on this graph, we can simply bring that line on the x-axis. So for instance, now if we have a new person and we know the height of that person lies between 70 and 80, we can project that point on this line and we would know what will be the weight of that person. So this is a very simple algorithm, one of the most basic algorithms that is used in machine learning. And yes, it is still used. And if you would see here, weight is equal to 80 plus twice the height. So this is a relationship which this algorithm has actually deduced from the data that was given to it. So initially we knew for the students, we knew their height, we knew their weight. And so we found a relation between the height and the weight, and this is the relation. So for any new height that you'll get, you can easily predict the weight of the students. So of course, you won't be doing it with your hand. This is actually done by a machine. So when you tell a machine to use this algorithm, this is the principle that it uses in the background. What are the common business use cases for linear regression? Well, again, sales forecast. You have historical sales of a product, and you would use linear regression to predict what are going to be sales in the near future. Another one could be optimizing price points and estimating product price elasticities, distributions, advertisements, etc. So these are common use cases which are used in industry, which people encounter in the industry, and they use linear regression for that. It's very interpretable. You can easily explain what is happening, why the model predicted a particular value for a particular data point. The next algorithm under supervised machine learning is logistic regression. Now, there's a catch. Even though, like linear regression, it also has a regression in its name, but it is used not for regression problems, but for classification problems. So this means that whatever it predicts has categories. So black, like it could only predict whether it is black or white rather than continuous. So why is logistic regression named so? So it is actually named after the transformation function it uses, which is called logistic function. So the function that you can see here is 1/1 plus e raised to the power minus. So this is called a logistic function, and hence the name is logistic regression. And this forms a S-shaped curve that you can see. So in logistic regression, what we essentially predict is the probabilities. So for instance, you have a problem where you have patients' data and they have tumors, and you have to predict whether a tumor is malignant or benign. So that's the problem that you have. So what will logistic regression do is give you a probability. So it will say there is a 0.7 probability of the tumor being malignant and 0.3 probability of the tumor being benign. And you have to take a call. So you have to decide a threshold. And for instance, you decide a threshold of 0.5. So anything above 0.5 would be malignant and anything below 0.5 is benign. Now, how do you decide on the threshold? This comes from a lot of factors, a lot of domain experience, and also what is more important for you. Should you it's okay for you if you wrongly classify certain cases, or you have to 100% classify all the cases correctly. So that way you have to decide. So there's always a trade-off, but you always decide on the threshold, and then you get probabilities, and then you take the final decision. So this is logistic regression. So again, some of the used cases where or the business cases where it is used is banks, again, where we have to identify whether a person is going to default or not. For cases like the one that I told you, whether the tumors are malignant or benign, or even you could say cases like sentiment analysis, where you have to identify whether a given text is positively or negatively sentimented. The third algorithm under supervised learning is decision trees. Now, as its name suggests, the algorithm takes a decision. And when it takes a decision, it clearly shows how it takes that decision. This makes it one of the highly interpretable classification or regression model. So this can be used both for classification problems or regression problems. What this does is it splits your data into branches at decision nodes. For instance, if you see here, this is a problem, for instance, where you have to identify whether a transaction is fraudulent or not. So the first decision that it will put is whether the amount spent in 24 hours is greater than the average amount that is being spent by the person. So if the amount isn't too big, then you would put another question, whether the number of states used were greater than 2. So if it's not, so again, you will say it's not fraud. But if it has been used from more than 2 states, you would say there's a 90% chance it's fraud. And similarly, you can have multiple questions like this, and you could increase the depth. This is called as the depth. You could ask more and more questions. But again, if you ask more, there'll be more questions. Again, there's a trade-off between interpretability or the time taken by the algorithm to execute and so on. Let's just not go into so many details. So again, as I told you, they're called classification trees if the final output that you're trying to predict is a category. So for instance, you wanted to know whether a transaction is fraudulent or not. So this is a binary problem. Again, if you wanted to predict some particular value like the sales price, that would be a regression tree. And together they are called classification and regression trees, or CART. Now, a decision tree on its own might not give you certain good results. And sometimes what we do is we bring together or we combine different decision trees. And this combining trees is called ensembling. For instance, you combine individual decision trees and you create a random forest, which is another algorithm which is used a lot. And so this is called ensembling. We'll go into details of ensembling in our next session, which will be held on Thursday. But for the timing, you can just understand or just remember that ensembling means to group the individual algorithms. And now it doesn't need to be only decision tree. You could ensemble a decision tree and you could ensemble another algorithm, logistic regression together. And it has been seen that they give higher accuracy. But if you talk about random forest, so a random forest would combine multiple random subsets of decision trees. Where are decision trees mostly used? They're used again in medical condition, the diagnosis, because it's of course interpretable. And secondly, it's used in credit scoring models, in which the criteria that causes an application to be rejected needs to be clearly documented. And this picture or the diagram that I'm showing you here on the slide is exactly how a decision tree works. And this is also, so you can output this, you can print this, and you can even show it to your stakeholders. So it's very interpretable, it's easy to understand, and you exactly know how an algorithm is taking a decision. Let's go to another algorithm. Now, why are there so many kinds of algorithm, you'll be wondering. So these are different kinds of algorithms, and it is for you to decide which algorithm you need to choose. So you have a library, and that library gives you a lot of options. And depending upon that, your problem, depending upon if you want higher accuracy, then you could use different kinds of algorithm. If you want interpretability and accuracy is not much a concern, but you want simpler models, then you can choose some different algorithms. So these are just the types of them which are available, and you can choose whatever your problem demands. So naive Bayes is a very interesting algorithm, and it's a classification technique actually that applies the Bayes theorem. And what Bayes theorem says is, it says that the probability of an event to be calculated. So what Bayes theorem it allows us is to calculate the probability of an event based on the knowledge of factors that might affect that event. So what does that mean? For instance, there's an email and it contains the words money. So what is the probability of that email being a spam? So of course, I think it's going to be high if an email contains this word money. So this is the way naive Bayes works. So it sort of tries to give you a probability of an event. So in this case, it would give you the probability that this email is spam, given the fact that it has money in its body or the subject even. So naive Bayes is used in sentiment analysis to assess the product perception in the market. Yes, for sentiment analysis and for NLP, deep learning is used, but naive Bayes is also used because sometimes deep learning models can be expensive, can be too memory intensive, and hence, depending upon situations, you can use naive Bayes, which give good results for text classification. You can also create classifiers to filter spam emails. Now, I'll just give you a small and very interesting example just to understand why this is called naive in Bayes. Now, Bayes is simple because it's based upon the Bayes theorem, and why it's called naive. Now, for instance, you have a data of 1,000 pieces of fruit, banana, orange, and there's some other fruit. And we know three features of those fruit. So long, short, long, sweet, and yellow. And depending upon them, we sort the fruits. So we have out of 1,000, 50% are bananas, 300 or 30% are oranges, and the rest of them, which is 20%, are these other fruits. So we know that this is the composition of our training data, for instance, if this is our training data. And now what we have to do is, if we are given a new fruit, can we identify, based on this data that we have, into which category, or what is the probability of that fruit being either banana, orange, or other? So we can use naive-Bayes theorem for that. And let's see how do we do that. So if we look at a data set again, from this data set, we also know something, that if you see in the banana row, out of the 500 bananas that we have, most of them are long. And then there are sweet, and then they're yellow. Again, for orange also, we have divided it into further, like 150 are sweet and 300 are yellow. And for other also, we have the features and we've populated that. Now, if we use the Bayes theorem and we just plug in all the values, so we will get three possibilities. We'll get the possibility of a new fruit being a banana, if it is long, sweet, or yellow. So you just don't have to go into this mathematics, but you just have to understand that we'll find three probabilities. Probability of banana being long, sweet, and yellow, and the probability of that fruit being orange, and the probability of this new fruit to be some other fruit. And we'll see which probability is the maximum. So whichever probability is the maximum, say it's maximum for banana, so hence we'll say that this fruit belongs to banana. And this is exactly what Bayes theorem is based upon. And when this Bayes theorem is used for classification tasks like this, then this algorithm is called naive Bayes. Also, it's called naive because all the features are independent of each other. So it's naive. And again, like the way I said, this helps us to calculate probabilities. So we exactly do not know whether this belongs to which a particular data point belongs to which category, but what we know is the probability, and then we can decide what is a threshold, and depending upon that threshold, we can assign that data point to a different category. And the last algorithm in supervised category is support vector machines, which is also called SVM. Again, SVM is typically used for classification, but it can also be transformed to perform regression. And if you see here in this 3D diagram, SVM essentially draws a division between classes and tries to make that as wide as possible. So you'll see for 3D, it creates a plane, and that plane is actually dividing the red and the green data points, and it's trying to put them in two different categories. So when a next point comes, it could be either red or green, depending upon which part of the plane it falls into. So this is typically used to predict how many patients a hospital need to serve in a time period. So these are some of the problems that it has been used, and how likely is somebody how likely is someone going to click on an online ad. So for them, SVMs are used. Again, this is mostly used for classification problems, like you can see here, and the concept. So what all these algorithms do is they try to create categories if they're classification, and all of them have different ways of creating that categories. So with this, we finish our supervised algorithms, where we saw what was a linear regression, logistic regression, decision trees, naive Bayes, and support vector machines. There are a lot of the other also, but we just touched on them for this session. The next category of machine learning algorithms that we are going to touch now are unsupervised algorithms. Now, like we mentioned, in the unsupervised, you essentially do not have a label or something that you want to predict. So the first one is K means clustering. So here K means has an importance because you try to put your data into a number of groups, and that number is denoted by K. And that is something that you can give. So for instance, you have this data here, which you can see on the screen. And I will give a number. For instance, I want to group this into maybe 4 groups. And so here K is going to be 4. And how will it group it? On some similar characteristics, which will be determined by the model and not by me. So what it does is, so here K is 4, and there are 300 data points. And so the model starts randomly selecting cluster centroids. So it will just select some random centroids first. You can see it selected the cyan, and then it selected yellow and selected a purple and maybe orange. So you have 4. So this is, it first just randomly allocates 4 centers, and then it starts as iterations. And once it starts as iterations, you see that the centroid changes. Now you'll have data points which are similar to this centroid will get collected here. The data points which are similar to this yellow centroid will get selected here. And similarly for purple and for orange, they will go. And when they go, you know, the centroid would change. So for instance, still you have yellow here, but now you'll see that this yellow are changing into cyan. And then it reassigns the data centers, the centroids, and again, it goes on till it has divided them into 4 separate groups completely, which could be discernible, which could be seen clearly. And so now we have this data set of 300 points, and now we have 4 clear groups in them, and you can also see there's a clear demarcation between all the 4 groups. If we would have given K equal to 5, then we would have got 5 groups. So again, we understood or we saw the example. So we would segment our customers by, for instance, it is if we can segment our customers into different groups by distinct characteristics. The next important algorithm that I would like to touch upon quickly, because I see the time is going past, is a principal component analysis, which is called PCA. And it is mostly used in those cases where you have a data set and you have a lot of features in them, a lot of attributes in them. And what you essentially do is you try to reduce those variables by just creating lesser variables, which can actually, in a way, explain the maximum variance. So for instance, if you see here, this is a 3D 3D graph, and what we essentially do is we just convert it into a 2D graph, and now we have 2 principal components, 1 and 2, which can actually explain all the variance of this entire data set. So this could be used when you have a lot of features and you want to reduce those features, you use principal component analysis. So this is essentially a dimensionality reduction technique also. Now, the last one is reinforcement learning. So here we don't have algorithms. I'm just going to talk about what I had taught. So initially also that how it works. So if you see here on the left-hand side, AI doesn't know anything about the game, and you see it's faring very badly. But on the right-hand side, the AI has learned how to sort of play, and now you see it's playing very well, the game of that classic snake. And also there was a news that Google's AI, it also beat a top player at the game of Go, and that is because of reinforcement learning. So how reinforcement learning works is you have an agent and you have the environment. So when you place your agent in the environment, and for instance, you see there's fire here and there is water. So if the agent goes to his fire, it'll get a penalty of minus 50 points. So then it knows that the next time it has to avoid that fire. And when it goes through repetitive iterations, it learns the concept of reward and penalty. And by this, it then learns how to play games or how to drive a car or, work for a specific task. For instance, we have robots. So that's the whole concept of reinforcement learning. With this, we come to the end of this session, and where we went through different algorithms of different kinds of machine learning types. And scikit-learn is a library, again, which has all these algorithms. So there's this nice picture which sort of differentiates all the algorithms depending upon the kind of data sets you have and the kind of problems that you have, depending upon whether it's a category or it's a number that you want to predict. Let's just quickly summarize what we studied today. We went over the different kinds of machine learning techniques and the different algorithms. And we also saw what kind of examples or business use cases could be solved by using them. I briefly touched upon the concept of ensembling. And in my next session, which is going to be held on Thursday, same time, I will discuss about some of the ensembling techniques, and also will touch upon the concept of automated machine learning, which is sort of known as the new wave of machine learning, also called auto ML. The quiz for this session would be available, and you can just go through them and earn a badge. And you can also attend our study group and Ask Me Anything group on the weekends. So that's all for me now. Thank you so much for attending the session.
Parul, there's a question. Do you want to answer it, or do you want me to kind of point it to?
Okay.
It says, can't see the unlabeled case in the selection.
So I did not, so which is the selection? I did go over the unsupervised learning and the scikit slide. Okay. No, there are, so if you see clustering here, clustering actually means the unsupervised learning. So you'll see there is k-means here and mini-batch and types of k-means. So number of categories. So this is also used for labeled data, but this is also used for, so they've given labeled here, but this is also used for unlabeled data as well.
Thanks, folks, for joining another session, and hopefully we will see you on Thursday for the next session. Have a great day or good evening.